So module number 4, clustering. So what is clustering? Clustering is a process of grouping a set of physical or abstract objects into classes of similar objects. So it is a process of grouping a set of physical or abstract objects. Physical means the one which we can see, and abstract objects are those which are hidden objects into classes of similar objects. A cluster is a collection of data objects that are similar to one another within the same cluster and dissimilar to the objects in the other cluster. So they are similar to the objects in the same cluster and dissimilar to the objects in the other cluster. Clustering, it is an example of unsupervised learning. Unlike classification, clustering and unsupervised learning do not rely on predefined classes and class labeled training. Example. So in classification we saw that classification relied on predefined classes and class labeled training. But in clustering and supervised learning, they do not rely on predefined classes and class labeled training. Clustering is a form of learning by observation rather than learning by example. So we'll see types of data in cluster analysis. So this is nothing but types of data in cluster analysis. So the first type is interval scaled variables. This section discusses the interval scaled variables and their standardization. It then describes distance measures that are commonly used for computing the dissimilarity of objects described by such variables. So the measures include the Euclidean distance, Manhattan distance, and Minkowski distance. What are the interval scaled variables? So what do you mean by interval scaled variables? Interval scaled variables are continuous measurements of a roughly linear scale. So they are continuous measurements of a roughly linear scale. Typical examples include weight and height, latitude and longitude coordinates. Example, when clustering houses, and weather temperature. The measurement unit used can affect the clustering analysis. For example, changing the measurement unit from meters to inches for height or from kilograms to pounds for weight may lead to very different clustering structure. So if you change the measuring unit if you change the unit from kilogram to pounds for weight, or if you change the unit from meters to inches for height, then it will lead to different clustering structure. In general, expressing a variable in smaller units will lead to a larger range of that variable and thus a larger effect on the resulting clustering structure. To help avoid dependency on the choice of measurement units, the data should be standardized. Standardization measurements attempt to give units. The data should be standardized. Why should be the data standardized? To avoid dependencies on the choice of measurement. So that you are not dependent on the choice of measurement. What should be followed? Standardization should be followed. A standard method should be followed. Standardization measurements attempts to give all variables an equal weight. So whether you take kg for weight, or you take pounds for weight, or you take meters for height, inches for height, everything will be given an equal weightage. Meter will be given an equal weightage, inches will be given an equal weightage, everything will be given an equal weightage. This is particularly useful when given no prior knowledge of the data. However, in some applications, users may intentionally want to give more weight to a certain variable than to the other. So in some cases, the user only wants to give more weightage to a certain variable than to the other. For example, when clustering basketball player candidates, we may prefer more weight to the variable height. So height will be considered a more weightage factor. Why? Because the more the height, the more your ball will go in the net. So height will be given a more preference, a more weightage. So variable height will be given a more preference. How can data for a variable be standardized? To standardize measurements, one choice is to convert the original measure to the unitless variables. Given measurements for a variable f, this can be performed as follows. So calculate the mean absolute deviation. So this is the formula for mean absolute deviation. Calculate the standardized measurement or z-score. This is the formula for z-score. Then you have formula for Euclidean distance. After standardizations or without standardization in certain applications, the dissimilarity between objects described by interval scaled variable is typically computed based on the distance between each pair of objects, and the most popular distance measure is the Euclidean distance, which is defined as, so this is the formula for Euclidean distance. Another well-known metric is the Manhattan distance. This is your formula for Manhattan distance. Both Euclidean and Manhattan distance satisfy the following mathematical requirements of a distance function. So distance is non-negative number. The distance of the object to itself is 0. Distance is a symmetric function. Going directly from object I to object j in space is no more than making a detour over any other object S, that is triangular inequality. So they follow these basic requirements are followed by Euclidean distance and the Manhattan distance. Euclidean and Manhattan distance you want to calculate if, so you have been given the coordinates and you have to calculate the Euclidean distance. So for Euclidean distance between x1 and x2 we'll do 3 minus 1 the whole square under root plus 5 minus 2 the whole square. So that is 2 square plus 3 square, that is 3.61. For Manhattan distance we simply just do 3 minus 1 plus 5 minus 2. So that is 2 plus 3, that is 5. So if you see the formula over here, you have a square root and here you don't have a square root for Manhattan distance. So next distance is the Minkowski distance. Is a generalization of both Euclidean and Manhattan distance. It is defined as, so this is the formula for Minkowski distance. Next type of variable is your binary variable. Let us see how to compute the dissimilarity between objects described by either symmetric or unsymmetric binary variables. So here they have calculated the Euclidean distance and the Manhattan distance. So we already saw this. Same numbers were there. 2 plus 3 is 5 and under root of 2 square plus 3 square is 3.61. So this they have represented it as half. You can also write it as under root, which is 3.61. A binary variable has only two states, 0 or 1, where 0 means the variable is absent and 1 means that the variable is present. Given the variable smoker describing a patient, for instance, 1 indicates the patient smokes while 0 indicates that the patient does not smoke. So in binary we know that there are only two values, that is 0 or 1. 0 means the event is absent, event is not occurring. 1 means event is occurring. So if there is a smoker, then 1 indicates patient is smoking, 0 indicates that the patient does not smoke. Treating binary variables as if they are interval scaled can lead to misleading clustering results. Therefore, methods specific to binary data are necessary for computing the dissimilarities. So how can we compute the dissimilarity between two binary variables? One approach involves computing a dissimilarity matrix from the given binary data. If all the binary variables are thought of as having the same weight, we have the 2 by 2 contingency table where q is the number of variables that equals 1 for both objects I and j, r is the number of variables that equals 1 for object I but that are 0 for object j, s is the number of variables that equals 0 for object I but equals 1 for object j, and t is the number of variables that equals 0 for both objects I and j. The total number of variables in P were q plus r plus s plus t. So what is the difference between symmetric and asymmetric binary variables? A binary variable is symmetric if both of its states are equally valuable and carry the same weight. That is, there is no preference on which outcome should be coded as 0 or 1. One such example could be the attribute gender having states male and female. So equal weightage is given to the males also and to the females also. Dissimilarity is based on the symmetry binary variables is called the symmetric binary dissimilarity. Is the dissimilarity measure defined as, so this is the measure for dissimilarity when the binary variables are dissimilar. A binary variable is asymmetric if the outcomes of the state are not equally important, such as positive or negative outcomes of a disease test. By convention, we shall code the most important outcome, which is usually the rarest one, by 1, that is example HIV positive, and if it is 0, then we say it is HIV negative. Given two asymmetric binary variables, the agreements of two ones is then considered more significant than that of two zeros. Therefore, such binary variables are often considered monary, that is, as if having one state. The dissimilarity based on such variables is called as asymmetrical binary dissimilarity, where the number of negative matches is considered unimportant and is thus ignored in the computation. So negative is considered as not at all useful. So we say that HIV negative, we remove that part. So we remove the negative matches and we only consider the positive matches. Next is your categorical variable. A categorical variable is a generalization of a binary variable in that it can take on more than two states. So in binary variable we had only two states, 0 or 1. But in a categorical variable you have more than two states. For example, map color is a categorical variable that may have say 5 states. So your map, in the geography we used to color the maps. So map color used to have many like red, yellow, green, pink, blue. Blue used to represent the oceans and the rivers. Green used to represent the valley or the ghats. Yellow used to represent the various plateaus. So this way we had different colors. Let the number of categorical variable be m. The states can be denoted by letters, symbols or a set of integers such as 1, 2 till m. Notice that such integers are used just for data handling and do not represent any specific ordering. How is dissimilarity computed between objects described by categorical variables? The dissimilarity between two objects I and j can be computed based on the ratio of mismatches. So dissimilarities is computed based on the ratio of mismatch. Where m is the number of matches, example the number of variables for which I and j are in the same state, and p is the total number of variables. Weights can be assigned to increase the effect of m or to assign greater weight to the matches in the variables having large number of states. Next is ordinal variables. A discrete ordinal variable resembles a categorical variable except that the m states of the ordinal value are ordered in a meaningful sequence. Ordinal variables are very useful for registering subjective assessments of qualities that cannot be measured objectively. For example, professional ranks are often enumerated in a sequential order such as assistant, associate and full for professors. A continuous ordinal variable looks like a set of continuous data of an unknown scale, that is, the relative ordering of the values is essential but their actual magnitude is not. For example, the relative ranking in a particular sport. For example, gold, silver and bronze is often essential than the actual values of a particular measure. Ordinal variables may also be obtained from the discretization of interval scale quantities by splitting the value range into a finite number of classes. Then we have the last type, that is the ratio scale variables. A ratio scale variable makes a positive measurement on non-linear scale such as an exponential scale approximately following the formula a e bt or a e raised to minus bt, where a and b are positive constants and t is typically represents time. Common examples include growth of bacteria population or decay of a radioactive element. So these formulas are used in chemistry. We saw that they were used for the decay of a radioactive element. How can I compute the dissimilarity between objects? By a ratio scale variable. There are three methods to handle ratio scale variables by computing the dissimilarity between objects. Treat ratio scale variables like interval scaled variables. This, however, is not usually a good choice since it is likely that the scale may be distorted. Apply logarithmic transformation to a ratio scale variable f having the values x, if for object I by using the formula yif is equal to log of xif. The yif values can be treated as interval values as described. Notice that for some ratio scale variables, log or other transformation may be applied depending on the variable's definition and application. Treat xif as a continuous ordinal data and treat their ranks as an interval valued. The latter two methods are more effective, although the choice of method used may depend on the given application. So later methods are useful, but you can also use the first method, that is treating it like an interval scale variable. But it depends on the choice of application where you are applying the ratio scale variable. Accordingly, you can use whichever method is convenient.